Specialty inks. Beyond the common categories, there is a world of specialty inks designed for unique effects or functionalities. These inks are used for novelty, security, or technological applications. UV visible and invisible inks. These inks either fluoresce under ultraviolet light or are invisible until illuminated by UV. UV-reactive fluorescent inks contain special dyes or pigments that absorb UV and re-emit visible light glowing under a blacklight. They can be colorful under UV, e.g. neon paints, or nearly invisible in normal light, used for security marking on documents or hand stamps at events. For example, an invisible ink might be a clear liquid that contains a fluorescing compound. When applied to paper, it dries clear, but under UV lamp it glows. Common compounds include stilbene derivatives or UV-fluorescent whitening agents. These inks are used in banknotes, ID cards, or fun applications like glow-in-the-dark tattoos, which actually use fluorescent ink that glows under UV, not truly phosphorescent. Speaking of glow-in-the-dark inks, those are slightly different. They use phosphorescent pigments, like zinc sulfide or strontium aluminate, doped with europium, that absorb light and slowly release it, glowing even after the UV light is turned off. Thermochromic inks. Thermochromic inks change color with temperature. They contain materials that undergo a reversible phase or chemical change at a certain temperature, altering their color. A common thermochromic system is a microencapsulated leuco-dye mixture. The microcapsule contains a leuco dye, which has a colorless state and a colored state. A color developer. At lower temperatures, the dye and developer interact to show a color. At higher temperatures, the solvent melts and the interaction is broken, turning the dye colorless. These inks can be formulated to change at specific temperatures, e.g., a mug print that reveals an image when hot coffee is poured, or a forehead thermometer strip that changes color with body heat. They are used for novelty items, temperature indicators, and security, e.g., packaging that shows if a product has been exposed to high temperature. Photochromic inks. These change color upon exposure to UV, sunlight, a bit like transitional eyeglass lenses. They contain photochromic compounds, often similar to those used in lenses, that are colorless in absence of UV, but develop color under UV. They can be used for gimmicks like an image that appears in sunlight and disappears indoors. However, their fatigue and longevity can be issues. Electrochromic and conductive inks. A niche but growing area. These are inks that change color when an electrical voltage is applied. Electrochromic, or inks that conduct electricity. Conductive inks. Conductive inks are used to print flexible circuits, RFID antennas, or wearable electronics. They often contain fine particles of metals like silver or carbon-based materials, graphite, graphene, carbon nanotubes dispersed in a binder. For instance, a silver nanoparticle ink can be printed and then sintered, heated or chemically treated, so that the silver particles fuse into a conductive metal track. Conductive inks allow electronics to be printed on paper or plastic. You can literally draw a circuit with a conductive ink pen. There are also conductive polymer inks, like PDOT, PSS, that are used for making things like flexible sensors or electroluminescent displays. Electrochromic inks, on the other hand, are a bit more specialized. They'd be layers in a device that change color when voltage is applied, such as an electrochromic display or window. Invisible and security inks. Apart from UV inks, there are inks that are visible but contain hidden features. Infrared absorbing inks used in currency, which appear black but have a specific IR signature detectable by machines. Magnetic inks, like the Micker ink used to print bank check numbers, which contain iron oxide, so they can be read by magnetic sensors. And microtagant inks, with microscopic encoded particles, are examples. These are used for anti-counterfeiting and authentication. Some inks only become visible under certain chemical or light conditions, so-called sympathetic inks. Historically, invisible ink for spy communications included organic fluids like lemon juice that turn dark when heated due to oxidation producing char. But modern security inks are far more sophisticated. Edible inks. Edible inks are formulated to be food safe for printing on edible paper, wafer paper, frosting sheets, or directly on foods, cakes, candies. They are essentially food coloring in an inkjet printable form. A typical edible ink contains water and ethanol as solvents, glycerin, or propylene glycol to adjust viscosity, and FDA-approved food dyes as colorants. For example, an edible CMYK ink set might use FD, C Red 40, Blue 1, Yellow 5, etc. Dissolved in a mix of water, 90%, ethanol, 3%, propylene glycol, 3%, plus perhaps a tiny amount of surfactant, e.g. polysorbate, to help wet the substrate. These inks are used in specialty printers to put images on cakes, often via sugar sheets, or to mark foods. They have to be flavorless or mild, quick drying, and safe to ingest. They also tend to be less vivid than regular inks, due to the limited range of food, dyes, and lack of harsh chemicals. Others. There are many more specialty inks for unique purposes. Etch-resistant inks, used in PCB manufacturing, as resist masks. Bio-inks, for 3D printing tissues. See Innovations section. Glitter inks, with suspended glitter particles for decoration. Fragrant inks, with microencapsulated scents released upon rubbing. Thermoset and silicone inks for ceramics and glass fired on. Anti-forgery gel inks that resist washing. If there's a particular need, chemists have likely formulated an ink for it. Learn more about art, history, and music at Oransbooks.com. Please like and subscribe, and may the rest of your life be the best of your life. Oran Z. Belgrave.